soc Marc.
Carlos.
Bueno, no, dic jo... Bueno, si vols dir-ho tu, en realitat. La porta està en l'ordre dels fastos, que la gent mire bastant, i la porta de fora, saps? La porta de fora, no sé. Si són de dona, la gent mira.
Hola? Ah, sí, se sent.
Si vols digues que pel matí tindrem 2 sessions de xerrades fins al coffee break, després una altra, no sé si vols dir alguna cosa més d'això i ja està. Dir hola a tot el món.
Bueno, lo he cerrado todo un poco. ¿Dónde estaba? Espera, Marc. Mira, sí. No lo he cerrado, lo que pasa es que lo he minimizado.
Sí, o sea, esta de aquí. Sí, el M2YRO Conference, ¿no?
No, això no.
Bueno, ponedlo, sí. Ponedlo, sí. Sí, lo he puesto ahí. ¿Lo he escrito yo?
Sí, empezás ahora...
Espera, lo he puesto. Hello? Hello, everyone. Good morning, and welcome to the second day of the M2YRO, the Mediterranean meeting of young researchers. So, the first one. Today we are going to start with 2 speakers. With Carlos and Alba, and you can check also in the door the guideline for the flash talks for this afternoon. That will be after the dinner. So, let me now introduce our first speaker, Carlos Doñate Buendía. He studied here in Valencia, in the University of Valencia, studied physics, and then the Master of Physics, focus on photonics. And after this, he moved to Castellón to start his PhD. And after finish the PhD, he moved to the University of Duisburg-Essen in German to start to make and synthesize nanomaterials as a postdoc. Recently, 2 years ago, he moved then also in German to Wuppertal, the University of Wuppertal, with the professor Bilal Gok, just to lead the group on nanoparticle synthesis and additive manufacturing. So now he is going to explain all his work in laser material processing and additive manufacturing. So now, Carlos, the floor is yours. So,
okay, thank you very much for the kind introduction. Okay, here you have it. Okay, yeah, so today I would like to tell you a bit, very generally, about many different topics. So you have seen that I started here also in this faculty already some years ago. Then moved to Castellón, then to Germany, and in all this trip I did different science, different research, going from, everything focused on laser, basically laser processing. And most of the time when you think about laser processing, you think about laser ablation, or you think about laser processing of surfaces to generate some specific patterns. But here I would focus more on the generation of nanoparticles using these lasers and using the material that can be ejected from our targets, and also about additive manufacturing. That is also quite a hot topic nowadays. And how we have combined also these nanoparticles that we can generate in the liquid to use them to provide extra functionalities to the additive manufactured parts. So first, well, I come from the group of photonics research group in Castellón. So there, as you have probably seen also, there are a lot of different topics involved. I'm more focused on the part of material processing and synthesis of nanoparticles. And apart from the material synthesis and nanoparticle synthesis, I'm bringing also from Germany, especially, my background also in additive manufacturing. And what's the idea, basically? Well, the general scheme that I will show you through all over the talk, it's this one. So what we like to do is to take our laser, do some ablation, generate our nanoparticles. So you see here a very easy scheme. What do we do with these nanoparticles? Well, we take them, and what we want to do is to take other materials that are used in additive manufacturing, like microparticles, like photopolymers, also filaments, and then add our nanoparticles. Why do we want to do that? Because if you are adding the nanoparticles, you are adding these properties that they have. For example, optical properties, magnetic properties, bactericidal properties, and also you can improve the basic properties of your base materials, for example, mechanical, and many more. Later, what should we do? Well, depending on the material that we have modified, then we need to print it. But the printing is basically done the same way as the standard material. So we don't need to, or what we don't want is to change the printing capability, because this is already developed for the industry. And the point is that if we change it, then industry won't like it, because we would need to adapt it again. So if we can use the same parameters, we can use the same devices that they are already using, and we only modify the material, then that's great, because they can directly implement it. Okay, so nanomaterials, maybe it's too general introduction in this case, but why are we interested in nanomaterials? Well, because this spatial scale is very interesting. For example, for bio applications, so we have that the nanoparticles that we can generate, that there is a wide variety. So from quantum dots that are nowadays very hot topic, even single metallic nanoparticles, oxides, carbon-based nanoparticles. And these nanoparticles have a size that is interacting with very fundamental bio units, let's say, like viruses, bacteria, but not only with medical parts, but also the interesting point of the nanoparticles are their functionalities. So when we reduce, for example, gold or silver to the nanoscale, we have this plasmonic absorption that is appearing. And then the characteristic color of gold and silver completely changes. So you see here, this is only silver in water, so we see this yellowish coloration. When we have gold, we have this reddish coloration. We can also, some other effects can appear. For example, for carbon, we have an interesting effect that's fluorescence. So depending on the size of our carbon nanoparticles, we can tune the fluorescence of the response of the nanoparticle, also depending on the surface group. You can guess, for example, that if the fluorescence depends on the surface, that's also a very good chance to generate sensors, for example, or detectors. Okay. How are nanoparticles done? Well, I will tell you about laser, but chemically can be also done, and in fact, it's a very interesting approach and very nice approach. And for example, the Nobel Prize in 2023 was awarded to also the developers of quantum dots by chemical processes, where they could control very nicely the size of the nanoparticles, and with that the optical properties and the emission properties. And these applications you see from quantum dots, nanoparticles of carbon, nanoparticles of metals, so we can use them in a very wide variety of applications, from nanomedicine, renewable energies, water purification, and generally what I would like to show you is material properties modification. What do we do with the laser? Well, it's pretty easy, in fact. So we just take a bulk target, or we take gold, for example, a target of gold, aluminum, any material that we want. An oxide, for example, can be also. We take the laser, we irradiate the target, and we collect these nanoparticles, the material that is ejected, in the liquid that we have. And that seems pretty easy. And in fact, if you see the video, for example, so the implementation is pretty straightforward. So we just place the gold target, we irradiate with the laser, and these are the nanoparticles that are generated. It can be done with gold. It can be also done with many other materials, silver, aluminum, any others. So we have a lot of versatility. And which are the advantages? Well, as you can guess, for example, when you are doing it with chemical methods, the problem is that you generate byproducts because you have a reaction, then you are generating your nanomaterials, but you are also generating extra materials or extra products. The point is that you need to purify those nanoparticles if you need to use them, for example, for biomedical applications. In our case, we only do the nanoparticles directly in water, so we don't have any extra chemical additive. The nanoparticles are quite stable because the surface charges are usually quite high. And if we want to functionalize them, we can directly do it in the liquid, so we can add the molecules that we want. Okay, with that, as a general point for laser ablation in liquid, so which are the disadvantages, right? Because if everything is good, then we won't be doing nanoparticles by chemical methods. We would be doing all of them with laser-based methods. So one of the problems is the productivity, the production rate. So here we did some review talking about the parameters that are limiting this productivity of the nanoparticles. And one of the first works, and the only work I want to show you today about the productivity, how we are planning to improve it, it's compared basically, or we were trying to reach the level of production of the world record that was achieved with a very specific laser, with a very fast scanner, scanning at 100 meters per second, and with a laser of 500 watts, a picosecond laser. So you can see, this is how fast you can produce the nanoparticles. And the problem of the productivity is always that when one pulse is reaching your target, you are generating a bubble. If your next pulse is not separated at a distance larger than the bubble, then this pulse will interact with the bubble and you will lose a lot of energy, and this will not go into ablation of the target, okay? That's the main idea. What we proposed, well, this is the standard system. We have the laser, we have a galvanometric scanner to scan fast because, of course, if we want to separate one pulse from the other, one strategy is just to go fast and move them quite fast between each other. Our idea was, okay, let's use a diffractive optical element. So in this way, what we do is just instead of having one spot, we are generating, for example, 11 spots. That's the case I want to show you first. You see here the implementation is pretty straightforward in this case, and you see here the ablated target. And what did we obtain? Well, here you see the increase. So we were having productivities of around 400 milligram per hour, 0.4 gram per hour for iron nickel. When we implemented diffractive optical elements with 6 beams and 11 beams, you see that we are increasing a factor 3 and a factor 4. Of course, this is not going linearly. It's not a factor 6, a factor 11, but there is some overlapping also between the beams. There are some shielding effects between the different areas of the beam. But you can see that going from 0.4 gram per hour to 1.6 gram per hour, sorry, was a huge increase. In fact, economically it's very important because going from these rates to these rates can make a complete difference in terms of the using of the nanoparticles in industrial applications. What were we doing? Well, when we have these bubbles, we want to separate one from the other, right? So if we optimize the system for one beam, for a repetition rate of 3 megahertz, here we have the maximum productivity, then we have a given interpulse distance given by the scanning speed of our galvanometric scanner. What happens when we use more beams? Well, the point is that if this is the optimized fluence, the optimized energy, let's say, what we want is to keep the same energy or fluence per pulse. How do we keep that? Well, we can just reduce the number of pulses, right? Now we have 6 beams, then we can reduce the number of pulses by 6, and we still have the same energy per pulse. But when we reduce the repetition rate, then the distance between pulses is larger because we are just removing, let's say, some pulses in the middle, right? So it's a very simple strategy, and it's avoiding you to require really fast scanning systems because moving from galvanometric scanner to a polygon scanner is moving like 1 to 200,000 euros in the price of the system. Here a bit of the scheme, a bit easy case. So we have one beam. I think I'm going. Do you hear me well? Yeah, because I think I'm not using it that much. We have here one beam. Okay. In that case, what we have are those pulses. and the same pulses are reaching the target, and they have some overlapping spatially. What happens when we have two beams is that if we don't change the repetition rate, the point is that we would have half the energy, right? And the overlapping will still be the same. But now, if we reduce the repetition rate by factor 2, here would be also half, then the pulse energy will be still the same, but let's say that we are removing one of the pulses, one out of two. And now the spatial overlapping will be higher, and that's what we are playing with to increase the productivity. Okay, overall, the numbers, because we like also the economical aspect, because we think it's important also to try to transfer technology to industry. So with the previous world records, so they were using 500 watts. We are only using 100 watts. They were scanning at almost 500 meters per second. We were at 20 meters per second. But you see that only using this diffractive optical element that goes like 1,000 euros, the difference between those two lasers just by the power, you can imagine, it's huge. It's hundreds of thousands of euros, and also the scanning system. So with those values, we are not reaching the same productivity. We are still at 1 gram per hour. Here is 3.8, but you see the investment. So it's like 1/3 or even less. And the power-specific productivity, so that's the productivity we get per watt, basically, and per hour, it's even higher than in the previous case because you have huge power. Okay, this is published already. First in this paper in Advanced Photonics Research, and later we were studying more the fundamentals because this overlapping between pulses is interesting to try to maximize it. Also studying how many beams we can use, what's the optimum, all these kind of approaches we were studying in this second paper. And from this side, I hope I have convinced you that this technique, laser ablation in liquid, it's a nice approach. Using the diffractive optical elements is a really easy approach to further increase the productivity without any more complex systems, because without increasing much the initial investment. Okay, and with that, that was the first part of the plasmonic polymers, but basically plasmonic with different optical properties. This can be plasmonic, but it can be also other kind of properties. It's only the point is that you can select the nanoparticle that you want, the material, and then make your combination. And also the photopolymers. So it's not only laser powder diffusion, but it's also we can also do it with photopolymers and adding nanoparticles with a specific distribution by modifying the printing area. So with that, I want to thank because well, all these results I started in Castellón in January, so all those results are not from Castellón, so are also from Germany, where I did my postdoc, and I want to especially thank my group there in Germany. Of course, the group of optics of photonics research in Castellón, where we are starting all these research areas, and we are advancing quite a lot, and I feel very, very welcome. And yeah, if you want to get in touch, so here you have different ways, and if you have any questions, I would like to especially thank the GENT program, because thanks to this one, I have been able to be back in January to Spain and start this research line here in Castellón. So thanks a lot for your attention.
Well, thanks, Carlos, for your amazing talk. And well, now we have a little bit time for some questions. But well, there are any questions in the room? Well, if you have.
Thank you. In the when you were showing the images of the bacteria growing, so you were comparing chlorhexidine, yeah, that one, with the silver nanoparticles. I'm wondering if you change the concentration of silver nanoparticles, could that help, or I mean, or not, or is there like a moment in which that a maximum of efficiency or something like that?
That's a very good question. In fact, we were surprised in this work because the concentration of silver was lower than they usually report to achieve this inhibition, because it's only,
Okay.
only 0.1% in the polymer. You can increase it indeed, and then if you increase it, you achieve higher inhibition or even bactericidal directly by touch. The problem of the silver is that after a certain concentration, it's toxic also for your cell.
Oh, okay.
So you want to keep a threshold where it's not toxic for you, but only for the bacteria. So that's the limit.
That's nice. Thank you.
Well, we have time for one more.
Gracias, Carlos. Yeah, maybe I missed it. I wanted to know a little bit on the rotor thing. I know it looks like some first results, but I was wondering if you know a little bit on the resolution you have on the rotation, like how precise can you be?
Yeah, that's true, because now it's mostly drifting, so it's not fully controlled the movement. That's something still preliminary on that. It's true that, for example, also the frequency, let's see, of the rotation is still a bit low. So in this case, we were not that interested in the fully control of the rotation and so on. It was more about telling the way, the process of generating the nanoparticles, adding to the photopolymer, seeing if it's feasible or not to print it with the distribution that could be actuated. Later we should go, but the idea to go in that direction from my side would be to increase especially the nanoparticle amount, because currently the forces are a bit low, but also the nanoparticles the concentration is pretty low. So then increasing it, you achieve higher forces, and then you can also control better the process, because then you could like change the magnet and then probably stop it and reverse it. But here I think it's still not making full sense to fully characterize the motion, because it would need higher motion or high speeds and so on.
Well, let's thank again Carlos for his amazing talk. Now we are moving to the next talk, and I pass the microphone to Luis to present our speaker.
So hello everyone, thanks for attending this second day of M2YRO meeting. I'm delighted to present Alba Paniagua Diaz, a postdoctoral researcher at Laboratory of Optics at University of Murcia. She obtained her PhD degree and in University of Exeter. His thesis title is Light in Scattering Media, Active Control and Exploration of Intensity Correlations. And currently her research is focused on improving vision and imaging through cataract research. So please let's give her a warm welcome to the stage.
Thank you very much, Luis, for the kind introduction. Can you hear me well with this thing? Okay. My name is Alba, and I'm coming from the Laboratory of Optics from the University of Murcia. And in this talk, I will be talking about a project that I've been working like for the past 5 years. Joined with, helped by different grants that I could have, that I have been like obtaining in the way. First, this is my trajectory. I started at the University of Salamanca. I did my physics degree in there. After that, I moved to University of Exeter, where I did my PhD. And right after that, I joined University of Murcia as a visual physics postdoc. This is the place where, the building. There are so many stairs that delivery doesn't climb there. Just deliver all the packages next faculty. But yeah, it's a nice place to be. There's a lot of research, and we are also in close collaboration with a company, a startup company from the group, that is Boptica, where I also spent 1 year working as optical engineer. So this is essentially where all this research is happening. Before we go into the details of the work, let me first introduce what cataracts are. I'm very well focused on vision, but from the physical side. Okay, so the cataracts is an ocular pathology that you might have heard of, probably. They approximately like 70% of people that is aged over 65 years old suffers it, and it is based on the opacification of the crystalline lens here, and it is because like the proteins of the crystalline lens, after some age, they because of degradation, there are some proteins that aggregate, and they like cluster, and by those clustering, that causes scatter, and when light passes through it, it scatters in all directions, and that leads to a blurry vision and low contrast. Currently, the only solution to that is surgery. There is no other way. The alternative to surgery is blindness, and in fact, these are responsible for more than 50% of blindness cases all over the world. Because here in Spain and Europe and developed countries, a cataract surgery is like a quite easy approach that most people can go through. Not everyone, but most of them. But there are many other countries where like surgeons are like not available, or the facilities and so on. So it's an important problem. So what we want to do, what we were wondering is, why don't we try to compensate for that scattering with some sort of glasses, right? Like in the case of myopia, if you have myopia, you can go for surgery and you can wear glasses. And in fact, most people prefer to wear the glasses. So can we pre-compensate somehow the scattering by using some sort of like smart glasses where we can like unblur those images? And this is the question that was raised many years ago, initially by Professor Pablo Artal, the group leader, and that I'm continuing since I arrived to Murcia. But before we dig into that, let's discuss very briefly what scattering is. Scattering is the process that happens when light encounters small elements of the size of the wavelength, roughly, and what happens is that different parts of the wave encounter different elements and then scattered in different directions, right? So it follows like a random distribution. So when light enters in this way, it just exits in all directions, like when you shine light through a piece of paper. So typical examples of scattering in our daily life are water drops. If you have water drops suspended in the air, as it is the case of fog, you cannot see clearly what is at a far distance, right? That's because of the scattering that light suffers traveling from the object to your eyes. Another example is sugar. We can be surprised by looking at a grain of sugar. A grain of sugar is transparent, but it is because of the roughness of the surface with the features of the order of the wavelength that makes it look like whitish, like ice cubes as well. So when you add many sugar grains together, they get like this whitish light, but that is because of light scattering. And last but not least, biological tissue, because of capillaries and mitochondria and different elements that we have in biological tissue, it scatters light. And in fact, it is like 10 times stronger than light absorption. Scattering is the main reason why we cannot see through our skin, for instance, and X-rays can. That's because of light scattering. And the same happens with cataracts. Because of these protein aggregations that I was talking about before, it is why retinal images look like blurry or with reduced contrast. And this is, well, a very extreme cataract, but and that's why it looks whitish. So now that we know what scattering is, the question is, can we control this scattering process? And the answer is technically yes. It was developed, like it was demonstrated, like in 2007 by Belekop and Musk, that it is possible to control the scattering process in some well-controlled scattering medium, and that is because most of the scattering that light suffers is elastic scattering. That is, there is no loss of energy, wavelength is the same, and the coherence of the light is preserved. That means that light propagation is determined by light interference. So if we change light interference, we can change light propagation, right? So if we look at it into a more detailed way, and we consider only two light paths, if these two light paths were originally in phase because they come from the same source, and they find the different elements on the way through the detector, if when they arrive to the detector they are in a counter phase, they can be getting with a destructive interference. If they arrive at the detector with a destructive interference, the intensity is 0. That intensity, as you know, is the square of the field, and the field in this case is the sum of the two paths. Now these two paths are characterized by their amplitude and their phase. Okay, that's important. So if we change the amplitude of the phase, we can change the field, and then we can change the intensity. So if we add an extra phase to one of these fields, we can make the two fields reach the detector in constructive interference. And by doing that, we change the intensity. So by changing the interference, by changing the phase, we can modify the propagation of light. Right. So if we do that for many fields, it is possible to move from a scenario like this, where light is scattered in all directions, to a scenario like this, where light, if we modify the phase or the amplitude of the incoming wave, we can use this scattering medium and focus light through it, for instance, and use it like an effective lens. Right. So what do we propose? Coming back to our original problem. If we modify the incident wavefront that is reaching our cataract or scattering medium, using like smart glasses, we could get a non-invasive correction of cataracts, right? And how can we do that? Well, the main actor here are spatial light modulators. These are like, I mean, the ones based on liquid crystals are the typical ones. And how do these devices modify the phase? Well, these devices are like an array of multiple pixels or cells, where each of the cells have some molecules inside. These molecules, if we apply some voltage to these cells, we can change the molecular orientation. By changing the molecular orientation, we change the refractive index, because they are very refringent. By changing the refractive index, we change the wavefront retardation. And by doing that, we end up shaping the full wavefront with up to 4K resolution. Okay, so we can have any wavefront shape that we want. And by using this device and adding it to like an augmented reality glasses architecture or smart glasses itself, we can combine this correction with ocular correction, right? And that's what we are after. But for doing this, we face three main big questions, right? The first question is, can we perform this wavefront optimization non-invasively? That is, can we know what is the wavefront that we should add to a patient by just looking at them without extracting the lens or anything? Because if not, it doesn't make sense, right? Can we image through real crystalline lenses? Because can we form images through these lenses? Because that haven't been done before. And if all this is okay, can we actually implement all this technology into a wearable system? So to form like some glasses. So we started with this question like a few years ago. And it is quite challenging. It is a quite challenging problem because we have several scattering surfaces. So if we want to measure the wavefront outside the eye, that is what makes sense, light travels, suffers one scattering event when it goes inside the eye, then it gets scattered again at the retina, and then it gets scattered again on the way out the eye. So it's 3 scattering events. So light information is absolutely lost in there. So that means that for getting the best wavefront, we cannot measure the scattering matrix of the lens. That has been some of the approaches that were on the literature, because essentially we cannot place a camera or a photodiode in the retina, right? And if we place it outside, light, as it is coherent, it just gets crumbled so many times that we lose all the information. We cannot place a photodiode for doing like iterative optimization. That was another option. However, there is something that we can use, and that is the fluorescence, the natural fluorescence of the retina. The retinal pigmented epithelium, it has some protein, the lipofuscin, that is that can be excited in the visible. So by using that, if we get that light that only goes through the scattering once, we can get some information on how the beam is reaching the retina. And that is what we did. We explored this option with an artificial eye because all our systems are so far slow slow enough as to not be used in patients. And so we used a silicon wafer as a diffuser, and we used a fluorescent layer with fluorescent emission similar to the one from the retina. And so we were exciting the fluorescent element, or like the artificial eye, with green light. And the output of this, I mean, the reflected fluorescence was passing through a dichroic mirror, and we placed a camera and a photodiode in a plane conjugated with the retina. So we were looking at the retina plane, but outside the eye. And we were filtering this fluorescent emission that was only going through one scattering event. So by doing this, this is the original shape of the incident beam on the retina, the coherent laser that we were going through. This is the output that we got from the fluorescent illuminated area at the retinal plane. And we chose one small area in there, and we performed our optimization. So we got a photodiode looking at this area and told the algorithm, okay, change the phase on our spatial light modulator so that the intensity on this spot always increases. And this is what the intensity is doing as the number of iterations of the algorithm increases. So as you can see, we got like a 58% increase in intensity, although we can do better, but it was like a 58% increase. And by doing that, we got to this point. We increased the intensity by using as a feedback the fluorescence from the retinal plane, and as a consequence, we shaped our incident beam reaching the retina. So as you can see, the PSF, or the point spread function, was pretty improved by, like, indirectly, by looking at an image of it. We, with this improved PSF, we did some simulations to see how this could affect imaging. This essentially was like a numerical calculation, so it's like a convolution of the object and the point spread function of the eye. So this is with an ideal PSF. This is with the cataract distorted PSF, and this is after the correction. And it was, I mean, it was a signal to noise ratio of 80. We can do better, but even that, we can retrieve some fine details and high frequencies of the images. So that demonstrated that it can work. We can improve images, which is fine. But in this case, we were considering that the optimized PSF was being optimal for the full extent of the image, which is okay for a simulation, but we are not sure if this is true for a real case, right? So our question was, how large can this optimized image be for our optimized PSF? Is the optimized PSF optimized for any angle that we enter the lens, or does it change? And or in other words, that is equal to ask ourselves what is the isoplanatic patch of the optimization. And this answer is given by the optical memory effect of the scattering medium. And it is highly dependent on the scattering properties of the medium. So we studied that, and this is essentially how it looks like. We with the optimized, this is the optimized PSF, and as we change the angle, as you can see, it disappears and it starts. It becomes optimized when you are close to the angle of optimization, right? So we needed to measure to know what is this area that we consider, where we consider that the PSF is still optimized. So we measured the optical memory effect of our cataracts. We did a long study in which Dulce there also participated as the end of degree project. So essentially we measured how the speckle patterns of the cataracts change, as we change the angle of illumination, and also changing the cataract laterally. And we took several speckle patterns, and then we do the cross correlation. And if the speckle patterns are the same, we get a nice high peak. And if they are completely different, we get just noise. So that is a way of measuring how similar or different two images are. So we did a measurement for like 34 different crystalline lenses with different cataract stages. And these are some examples of this. In the y-axis, we are showing the normalized cross-correlation. So it is maximal if the two speckle patterns are exactly the same, and it decays as the speckle patterns become different, meaning that our optimization would be lost. So the stronger the cataract, the faster it drops. The weaker the cataract, the more time or the more angles it's, in other words, the wider the optimized image can be. That is for tilt, so angular change, and this is for shiftings, for lateral displacement of the crystalline lens. Whereas we have fixed illumination. These are like some examples for cataracts of different grades. So this is a recently clear cataract, medium, and this is a very severe cataract. So these are images through the lenses. So as you can see, the contrast is worse as the cataract strength is larger. Here we saw the PSF, which spreads as the cataract is more opaque, and these are dark field images. And here we saw how the scattering, this is the scattering strength growing in this direction, and this is how the Michelson contrast of the images is well related to the scattering. So the more scattering, the less contrast, as we can see here. This is how it changes for the degrees and the shift. But this is the important graph where we show, we look at half the correlation. So when the peak of the correlated speckle patterns drop to half, we consider the speckle patterns are decorrelated, so that we consider that they are different. And so what we see is that the stronger the scattering, the smaller the angle for the correlation, okay? Again, as I said, the more scattering we have, the smaller the optimized image. That is the conclusion. So the conclusions from this first part were that the wavefront can be optimized in a non-invasive manner, that the wavefront optimization is valid in a small angular region, which is our isoplanatic patch, and that is given by the optical memory effect of cataracts. And last, the size of this isoplanatic patch is dependent on the scattering strength of cataracts. So with this, we answer to the first question. We can perform the wavefront optimization non-invasively. So this idea could be successful, right? So the next question was, can we optimize images or PSFs through the real cataractose crystalline lenses? And these are our very recent results. These are unpublished still. And what we were doing here, we were using a spatial light modulator, DMD in our case, a digital micromirror device, but it was modulating phase and also amplitude. We were playing with both options. And in a conjugate plane with this, we have a mirror that can move in X and Y. I'll tell you later why. And also in a conjugated plane with that, we have our crystalline lens that forms our artificial eye. We have as a retina camera in this case. We know we can do it non-invasively, so this option is just faster and easier. And we were using real crystalline lenses from human donors. We are collaborating with a local hospital that they provide us with these lenses. And we just leave the cataract developed as part of the rotting process of the lenses. So this is how our lens looks like. So this is our object, and this is how this is the image of that object using that lens. So essentially, a person with this cataract is considered like clinically blind, okay? Because I mean, they cannot differentiate anything, just shadows, okay? This is the PSF of this lens. And this is how it looks like after the optimization. The PSF enhancement factor, or the signal-to-noise ratio, is 72. If we zoom that in, we see a clear difference in here. So after we have performed this PSF optimization, we have concentrated most of the light in that focal spot, right? And yeah, so we were only using 500 iterations of the algorithm, so it's something that can be still improved. And this is how our PSF looks like, again, when we change the angle. This is a representation of how this optimized peak changes as we change the angular orientation. If we consider again that our PSF is optimized when the peak drops to 0.5, this is the isoplanatic patch of our optimized, maximal optimized image for that highly cataractose lens. If we convert it to degrees, because in vision we don't talk about an image size, but an angular size, it is about 0.68 degrees, which is not a lot. But as we saw before, it depends on the cataract strength. If the cataract is weaker, we get this will be larger. We can consider like that part of the image as our isoplanatic patch, like the maximal size of our image. But in vision, that might look, I mean, 0.68 might look very small, but although we have like a 200 degrees visual field, roughly, the central part, that is the high resolution one, is about 5 degrees. So it's not very large in comparison, okay? And in fact, if we took a picture of how we see in our full visual field, it would look like this. We have a small region where we have high resolution images, and the rest, it is like that. Although we don't perceive it like that. We perceive that we have high resolution in the full field, right? But that's not right. And the reason why we can see in all directions with high resolution is because we move our eyes. So by moving our eyes, we are scanning with this high resolution area the rest of the field. And just an approximation so that we can get an idea of what these visual angles are. 1 degree is like if you put your hand far away and you look at it, that is 1 degree in your visual field. These are like 5 degrees, these 3 fingers. Roughly, that's an approximation, but it helps us to figure that out. So that is the high resolution areas that we have. So knowing that, we used our XY mirror to draw things, right? So we scanned our optimized PSF, and we were drawing circles in this case. So this is a circle with this diameter, 0.3, that is inside our isoplanatic patch. This is a bit larger, almost close to the limit, and this is about 2 degrees, which is outside our predicted isoplanatic patch, but still we can see that circle quite clearly. And after doing this, we thought, okay, it's okay. We can draw simple things. Let's draw something that is larger. Let's explore the limits of this, and let's draw letters, right? So these are the examples of how this is being drawn. As I said, we have like the XY mirror, and we scan the optimized PSF, and here is just the scanning of the non-optimized one. So here you can see the big difference between the optimized and non-optimized case. And then by time integrating this is what we obtain. So essentially we can, very far from our predicted isoplanatic patch, we can still recover letters. We can still read, and essentially for a person with this sort of cataracts, we can retrieve vision. So we can use this approach for improving vision, for forming images through that cataract. And I have to say that for this reconstruction, we were only using one optimization, one PSF optimization. This can be highly improved, and we are working on that. If we optimize the PSF here, another one here, another one here, and so on. If we have several PSF optimizations, we have several isoplanatic patches where that we can collapse like in a mosaic structure. And by doing that, we can get much better and higher contrast images reconstruction. So I was doing that with phase, as I said, but as I mentioned at the beginning, we can also improve, do the wavefront shaping by amplitude modulation, right? Because we have two of them, and this is how essentially how it works. we saw that by adding an extra phase, we can move from a destructive interference to constructive interference. Now, if we have a destructive interference of these two paths, and we cancel out one of them, we can still get some intensity out. So we can improve the intensity that reaches by just canceling out one of the paths. So this is amplitude modulation, essentially. So the good thing about amplitude modulation is that amplitude modulators are quite cheaper, and they can be much faster than phase modulation with more pixels available, and so on. So it has some good advantages. So we did this for the same number of iterations of phase, so to have like a fair comparison. And by doing that, we increased the PSF by a factor of 24. It was like 3 times less than phase. Phase is more efficient, but as I said, this amplitude modulation has also some advantages. And another one is that it is faster. The optimization is faster, so we can also play with that. And by doing that, we also were drawing some circles. At this point, it starts failing. Now, these are the same sizes as before. And we also tried to draw some letters. Again, this is worse than the previous case, but it is not clear if it is because we have a smaller enhancement factor, a smaller signal-to-noise ratio, or it is because of the modulation type. I think it should be because of the small enhancement factor, but that's something that we have to try, and we are willing to try. These are just results from last week, so we didn't have time to explore it more. So for this part, we conclude that we can focus light through human crystalline lenses efficiently using phase or amplitude. We can successfully image through cathode lenses. And there is still a lot of room for improvement, as I just mentioned. Also, like improving the PSF optimization that we just limited because of time, but we can the optimization is still growing, so we can still improving the PSF, which will improve images for sure. So we answered to these 2 questions. Now the third question and the last question in a fast way is that can we implement this technology into a wearable system? And this is a bit of work in progress. We designed an optical system, a small optical system, to integrate all this technology, all this light shaping into like this part of the glasses, because we want to integrate it into like augmented reality glasses. And this is the first prototype design. It's big, it's not very nice, but it has some good things. First of all, it works with a Raspberry Pi. It's not optimized in space, but it is wireless. These are the pictures from the constructed device. And the good thing is that it doesn't occlude the visual field. So it's only you have like a clear visual field, and in addition to that, you have an image that is coming from this beam splitter, from this beam splitter here. That is this one here. So you have an extra like image, and the idea is to use this display screen to display the image of a camera that is placed in here. So a camera is recording what is outside, and that image is being displayed in this image, in this screen, and then is modulated, corrected for scattering, and then is sent to the eye. We have experience doing this sort of modulation for correcting myopia, presbyopia, high order aberrations in the eye, and so on. So this is essentially the same. We can be modulating the face, but now for scattering correction, right? So this is a device that, we haven't taken images yet. This is our first attempt. It is easy because the system is simple. But the next step that we are also like exploring in parallel, we bought one of these evaluation units from Dispelix that is based like for augmented reality, and they are based on waveguides. So the idea is to have this sort of glasses where they are like transparent glasses, but a screen in here is like a window where you get your augmented reality image that in our case would be like a video, a corrected video of the outside, overlapped with the outside world. And by leading it to with this device, it leads it to the eye in a like a more aesthetic way. So this is all with this. I think I have answered to these three main questions. Now the future plans are to optimize the wavefront correction and the glasses design, of course. We are in the first prototype and with economic components. Study the integration of an XY MEM mirror into these glasses, or to also explore other alternative imaging approaches. And the bottleneck to move really faster with patients and so on is the speed. So we need to speed up the measurement process of the wavefront that is needed for correcting scattering. And the idea would be to have like a desktop system where we can measure the wavefront very fast and also use it for the calibration of the glasses. So the global conclusions of the talk is that well, imaging through cataracts is enabled by both amplitude and phase modulation. That we demonstrated some time ago that non-invasive wavefront measurements are possible, and well, although it was achieved with artificial eyes, it tells us that it is not limited by any physical reason. It's something that we can achieve. And this technology can also be implemented into a wearable system based on the augmented reality glasses architecture. And there's a lot of work to do. And the main bottleneck now that we're facing is speed, and we are also working on a more wearable design. So with this, I thank you all for your attention. And I thank also the M2YRO group because in the end these long-term projects and works are always, they need to be supported by a long team, big team, by like computer engineers, optometrists and so on. So yeah, so thank you.
Thank you so much, Salva, for such an interesting presentation. Now it's time for questions. Do you have any? Is there any question? Okay, I will go first.
Bueno, muchas gracias por la charla, Alba. Ha sido fantástica. Ayer hablando con Dulce y su TFG y sus resultados, le preguntábamos a ella, ahora te pregunto a ti, a ver si habéis conseguido algo más. Las medidas, al menos las que vimos, estaban hechas en cataratas nucleares. ¿Habéis medido en otro tipo de cataratas?
No. Buena pregunta. No hemos medido en otro tipo de cataratas porque no las hemos conseguido. Sin embargo, las cataratas nucleares son las más comunes y sí que hemos pensado en la posibilidad de las cataratas corticales, que son inhomogéneas y demás. Para eso estamos trabajando también en colaboración con Enrique Tajoaurce en Castellón, y con la idea de, creemos que la idea más eficiente para atacar ese tipo de cataratas es modular la luz para meterla por los agujeritos que son transparentes. Podría ser más eficiente que esto, pero sí, tenemos que probarlo. Hemos intentado generar cataratas corticales con láser, generando scatter, como un poco como quemando el cristalino, pero no hemos conseguido un scatter controlado. O quemábamos el cristalino y se rompía, o era muy opaco, o no hacía buenos efectos. Entonces, bueno, ahí estamos.
Vale, gracias.
Professor, you have a question? Hi, very interesting talk. I think my question goes to your, I guess the final conclusion, right? One of the potential problem that you see is that you need a higher speed.
For measuring.
Right. I may have a different opinion than that, right?
Okay.
Right. So if I understand you correctly, the reason for demanding a higher measurement speed is because you want to track, basically if, for example, the clear vision is only provided in ±1 degree, and you're trying to see something that's beyond that, then you need to correct the wavefront in almost like real time, right? Is this why you need such a high imaging speed or measurement speed?
Not really. The main problem is that when we are optimizing the PSF. When we optimize the PSF, we need the feedback from the retina, and we optimize the PSF in an iterative way. So we need to measure like 6 values of intensity for each iteration. And we need to do at least 500 iterations. So that is a lot of I get the intensity, I store the intensity for 6 times, and then after I have like all these 6 intensities, I evaluate what is the best intensity, I choose that, and then I generate new patterns, new phase patterns, and I test it, and then like that for 500 or 1000 iterations. And that is the slow part. So right now we are doing it very slow. We are not worrying about that very much, but it takes us like 15 minutes. You cannot have a patient with the eye open for 15 minutes. That's the problem. We know that it is possible. Rafael Piestun and company, they managed to do optimizations in 2.4 milliseconds. So it is not limited by physics or engineering, let's say, but in our system we are slow. What you said, that when you are looking at different places, our idea is you once you have the optimized wavefront, you can optimize wavefront in different regions, so you can have like a wider isoplanatic patch for a wider image. And once you have that, you can also have to store it for different gaze directions. And once you have the optimization, you can have a relatively static wavefront display on the glasses, on the wearable system. But you need the speed for the measurement, for the first
I see.
optimization.
So this part I understand. But I mean, what did you didn't talk about for the wearable design is about the eye tracking.
Yes.
Right. So I mean, I think right now, let's say Facebook or other big companies, they can actually track the eye at roughly 1 kilohertz.
Yeah.
So is this part of the design that you're about
Yes.
to do, or okay.
Yeah. I mean, there are other things that I didn't have time to mention either, but yeah, this the idea is to have a couple of pupil cameras for eye tracking. In our group, there are also, I mean, we do several like wearable systems, and they already have the technology for real-time pupil tracking. And by doing that, we can know where the gaze is looking at with a very good precision and in real time. So that is something that, yeah, it's in mind. And also another thing is that we use a display because scattering correction is highly wavelength dependent. So we cannot correct for full spectrum image. It's like crazy because you need a different wavelength for each different, a different correction for each different wavelength. So we plan to use an RGB screen so that we can optimize 3 colors, and then multiplex it in time. And
okay, yeah.
so
I mean, this is actually my last question. I mean, for your method to work, right? It seems that you need a coherent light so that you can control the wavefront. But I mean, do you see any challenges if you want to use, let's say, a RGB laser diode to do your display, right? Is that a requirement, or I mean, do you have any requirement for the light sources that you want to use for the display?
We are actually using laser diodes. So it's the coherence in that terms it's kind of okay. There are papers from ORICAT where they demonstrate that as long as after you have the optimization with coherent light, as long as the optimized, I mean the incident light has the same wavelength, it doesn't matter if it is coherent. If you add a phase to an incoherent light that has the same wavelength than the one that you optimized previously, it should work. So it should work with incoherent light as well. But that is something that we plan to try in the next weeks or months. But even if that doesn't work, that is not a big problem because we were thinking on using laser beam scanning technology for display. There are displays that are based. They have 3 lasers, RGB, and as long as you optimize the wavefront for these 3 wavelengths, they essentially create the images by raster scanning, as we were doing before. We were creating the image by XY raster scanning, and that is a technology that is used for displays as well. And they are also very common in augmented reality glasses, so they are already like very compact. So that's a technology that we can use. We try to buy them, but they are offering us like 100 or 1,000 units. And when we say that we only want 1 or 2, they say they are not interested. So, but yeah, that's something we want to try.
So thank you very much, Alba. It's time for moving for the coffee break. Let's thank Alba again. Just one moment. We have coffee break now. At 11, the next local